So welcome back to section 4.2, talking about finding the zeros of polynomial functions. Looking at this example here, if I asked you to find the zero of this function, you'd want to go through and start using your factoring techniques, but it's got 5 terms in it, and factoring when it has 5 terms in it is rather difficult. You could try to pull out the greatest common factor. There is not a greatest common factor for this problem. But notice that you're also given a 0, and that 0 is an imaginary number, or a complex number actually, part imaginary, part real. So if you're given a 0 that is a complex number, its conjugate will also be a 0. So for this example, it would be 1 minus 3i is also a 0. And what I know is that zeros should divide evenly into the polynomial. Well, these are imaginary numbers, and if I multiply them together as the factors together, that answer should divide evenly into here. So let's first write these as factors. We would do x minus the 0. Which would really make it become x minus 1 and then minus 3i. And over here it would be x minus 1 and then plus 3i. So if I multiply these together, I'm going to get a degree 2 polynomial that will not have any more imaginary numbers in it. That polynomial will divide evenly into here. So let's multiply these together. So I'm going to make this table here to help me multiply these together. So multiplying together, I'm going to get x squared minus x plus 3ix. I'm going to get negative x, positive 1, negative 3i, negative 3ix, positive 3i, and negative 9i squared. Now more than likely your like terms are going to be on the diagonal, like so. Those are like terms, those are like terms, these two are like terms, and also these two are like terms because negative 9i squared is the same as a positive 9. So when I combine like terms, I'm going to get x squared. I'm going to cross it off so I don't try to use it again. Negative x minus x is negative 2x. These imaginary terms should cancel each other out, so that does, which is good, and these two do, which is good. And then finally you have 1 plus 9, which is 10. Again, you get a polynomial that has no more imaginary numbers when you multiply conjugates together, which is exactly what I did. Now this polynomial should divide evenly into here, and to do that we have to use long division. So let's set that up over here. Take the polynomial, divide it into the original polynomial that you were given. And remember, here's how you do long division. You just deal with the first 2 terms. So this term here and this term. So instead of the first 2 terms, it's the first term of this polynomial, the first term of this polynomial. You ask yourself, what do you have to multiply x squared by to get x to the 4th? Well, that answer would be x squared. Then you actually take this x squared and you multiply it by all 3 of these. So x to the 4th minus 2x to the 3rd, and then plus 10x squared. And now we subtract. Remember, we're subtracting each of these answers. The first one will cancel out. Negative 3 minus negative 2 is like adding 2, so it'd be negative 1x to the 3rd minus 4x squared. Drop down your next term. Start the whole process over. What do you have to multiply x squared by to get a negative 1x to the 3rd? And that would just be a negative x. So multiplying all of these by negative x, you're going to get negative x to the 3rd. You're going to get positive 2x squared and negative 10x. Again, we're subtracting. These will cancel out. This will end up being negative 4 minus 2, so negative 6x squared. And this will be 2 minus negative 10, which is like adding, so it'd be positive 12x. Drop down your last term. And again, start the process all over now. What do you have to multiply x squared by to get negative 6x squared? That'll be negative 6. So multiplying all of these by negative 6, we get negative 6x squared, positive 12x, and negative 60, which is good because I got the exact same thing I already had. So when I subtract, everything will cancel out. I'll get a remainder of 0. I needed to get that remainder of 0, otherwise I didn't do this right. Because these were conjugates, and when I multiply that out and they're zeros, they need to divide evenly into my original problem. So now I'm at the point where I need to actually, because it wants me to find the zeros, I need to find the zeros of this function. So let's write that over here. So this is a degree 2 polynomial that I can factor. Ask myself what multiplies be negative 6 and adds to be negative 1. That would be a 3 and a 2 where the 3 is negative. So x minus 3 and x plus 2. And again, if I set these equal to 0, I end up with a positive 3 and a negative 2. And then I want to go back up and make sure that I did what it asks. It says find the remaining zeros of the polynomial. Well, there should be 4 zeros altogether because it's degree 4. I was given 1. 1 plus 3i. I found the other one because it was a conjugate. 1 minus 3i, and I just solved for the other two. 3 and negative 2. So those would be my 4 answers. Okay, for this next problem, we're actually going to work backwards. We don't have the polynomial function, instead we have the zeros of the function, and we are trying to come up then with that polynomial. So one thing we have to remember is if we have imaginary numbers, or excuse me, complex numbers, which this is a complex number, that its conjugate is also a 0. So I've got 1, 2, 3, 4 zeros altogether, so it should be a degree 4 polynomial. So if I'm going to try to find the polynomial, I have to write these zeros as factors. So I'm going to do x minus each of the zeros. So that would look like this: x minus negative 5, x minus negative 5 again, x minus 1 plus I square root of 3, and x minus 1 minus I square root of 3. So let's do a little bit of simplifying here. This is really an x plus 5. Same with this one. This one, when I distribute this negative in, becomes x minus 1 minus I square root of 3. This one will become x minus 1 plus I square root of 3. Whenever you're dealing with conjugates, when you do the multiplying, multiply the conjugates together first. You're going to get the imaginary numbers to go away, which is going to make your problem a lot easier to deal with. And then likewise, let's multiply these two together to FOIL, or by foiling, and then we can take those two answers that we get and then multiply those together as well. So if we FOIL this, we end up with x squared plus 5x plus another 5x plus 25, which would give me x squared plus 10x plus 25. Now let's multiply these two together. Again, I'm going to make a chart for this because it's going to be easier, I think, to multiply these together. Keep in mind, when we multiply conjugates together, that we should not have any more i's left over. So multiplying here, we get x squared minus x minus I x squared root of 3 minus x plus 1 plus I squared root of 3 plus ix squared root of 3. Made my box a little too small there. Minus I square root of 3. And finally, I times negative I is negative I squared. Square root of 3 times the square root of 3 is 3. So this really becomes, when I deal with the negative I squared and the 3, this would become a positive 3. So combining like terms, this would be my x squared. It has no like terms here. These two are like terms, minus 2x. The positive ix square root of 3 will cancel out with a negative. The negative I square root of 3 will cancel out with the positive, and then 1 plus 3 is 4. So now I have this polynomial and this polynomial left over that I need to multiply together. So I'm going to have to make myself another chart here. X squared plus 10x plus 25. Let's take this one and write it horizontal or vertically like this. Okay, now multiplying this together, we would get x to the 4th plus 10x to the 3rd plus 25x squared minus 2x to the 3rd minus 20x squared and minus 50x plus 4x squared plus 40x plus 100. Now again, my like terms should be on the diagonals. You'll notice that that's the case here. So we'd get x to the 4th plus 8x to the 3rd. Then this would be 29. 29 minus 20 would make 9x squared. And this would make negative 10x plus 100. So this would be the polynomial that would have the following 4 zeros: negative 5, 1 plus I square root of 3, and 1 minus I square root of 3. Again, remember we stated at the beginning it should be degree 4, and it is. So we know we did that right.